Doing it time after time. I thought I'd try to develop some tools to try to find these problems while the system call was still in the development phase before they actually ended up being deployed in end-user systems. The idea of a system call fuzzing isn't particularly new thing. There's one example I have here of a tool that kicked off Susan wrote back in 2002, I think it was. And it's very simple and basic. Basically, what we have here is call a bunch of systems. This is a system call number. And these are the parameters that get passed into that system call. And as you see, it's just completely random numbers. Just doesn't mean anything at all. So, unsurprisingly, on the right-hand side, you see that you just get bad addresses and public parameters. So most of the time, the kernel does the right thing. It just rejects the input. When Kirk first wrote this program, the kernel hadn't had any kind of testing like this done to it, so it wrote a whole bunch of stuff, which was fixed up very quickly. But because the tool is so basic, I mean, this is all it really does. After those initial bugs were fixed up, that was pretty much a done deal, and the tool was pretty much forgotten about for about the last 10 years. So last fall, at the kernel summit, it actually brought up the point that I actually made that we kept reintroducing new security calls and system calls that we were adding. So I decided to revisit this and try to make it a little smarter. So, oh, this is going to be fun.
Is this Fedora 50?
Anyway, so first rule I wrote pretty much does exactly the same thing. So this is the tool that I wrote. It's a little more verbose. It actually tells you what the system call you're calling is, what the parameters are, and again, it's just passing random crap to the actual parameters. And you see the return in green means the system call succeeded. The color in red is not a failure. Not that it really matters, because if you still get a crash in the system call, even if it succeeds, it can still be doing something like right on the side, array boundary, or one of those ones. So this was the most basic operation, which does nothing really, nothing exciting that Kurt's initial tool did. So this found a few bugs, again, even though we've done exactly the same thing as the old tool. I think it's just that no one had been doing anything like this for so long, so just revisiting that whole technique of finding old bugs turned up a whole bunch of little silly, like off by one bugs and stuff. So the next day I added a different mode where sometimes, instead of just passing random garbage, I started passing things like a 0, just to see if we can trigger nullity references, where we missed out a check for 0 in the happened. And to do this, the way this works is, I'm going to use a really good example here, but if you imagine the parameters, the 6 parameters there. The first thing that this mode does is it passes a 0 in the rightmost parameter, then it'll pass it in the secondmost, then it'll pass the 0 in both of those, then it just works its way along until eventually it passes a 0 in every possible combination of parameters. So adding this mode, that turned up another bug or two. So at this point, I'm starting to realize maybe this is actually worth putting more time into, because it seems every time I add a new mode to this, I'm turning up new bugs. So, even though I was turning up bugs, once those were fixed, it would get to a point where I just run this tool over and over and over for a day, and it still wouldn't find anything new. So, it needed to be a little smarter. And most of the time, you just see it just rejecting, because the first thing the kernel does is, if it's expecting, for example, a file descriptor, and you're passing in just random junk, you'll just reject immediately if this isn't a file descriptor. So I decided to make it a little more intelligent by actually passing in a file descriptor when it wants a file descriptor, and still looks actually. So on start, when it's in input mode, the first thing it does is generate a bunch of random sockets with various different protocols and domains and such. So it's completely, well, random. It generates a few hundred of those, and then it picks up a whole bunch of random files from sysfs and procfs and /dev, just to have a bunch of actual FDs to pass around. And then it actually does exactly the same as it did in the previous example. But now, for example, if you look at the set X error, FD being passed is now 12 rather than just random, right? In fact, all the blue numbers now, these are all numbers where the tool knows what this kind of argument is and is passing something that it knows about. Like, notice page is trying to wants an address. So it's passed a page filled with that value, X, FF. This one is passed a page just filled with random garbage. It's actually passing real addresses around now. The downside to all this is actually a lot of groundwork actually annotate every different system call to explain to the tool what to pass and how to get deeper into the function call. So for every single system call, I have these definitions which look kind of like this. This is a simple one. The fork system call. We have just the name of the actual system call, the number of passes it makes, and we have the flags for every system call. This one we want to avoid, and this tells the tool not to ever call the system call. Don't ever call the system call because you're doing a random thing, you could end up just fork-bombing computers. There's certain other system calls as well we want to avoid for similar reasons. So that's the very basic one. Your question?
Yeah, well, just on the subject of like memory case, okay, what about like, so you're mapping you're mapping a bunch of memory that you use for the address comparison is actually a legitimate address in the address space of that process. So what about like, you might get to this, right? But what about like passing an address that's in the last page of the address space that's like high towards the end of that last page, so it's likely to go into the following page or something like this. Do you handle that sort of case?
I do. I'll kind of touch on it in a minute. If I don't fully answer your question when I explain the annotation, then elaborate.
Cool.
So that's the fork case, which is a very simple thing. A more complicated one would be so M shows you there the second argument. This is a length. So when it sees that when it's answered with a length, we do things like what magic function here we have is get interesting value. And the interesting values we do all sorts of strange things here. We pass things like close to the 32-bit boundary, just really weird magic numbers. Yeah, just really strange things that may actually trigger some sort of boundary cases where people are doing sort of a comparison for greater than what they should be doing, greater than equal, that sort of things. And that's actually triggered a fair percentage of the bugs that it's from, which I'll show in a minute. 64-bit case does exactly the same thing, but it's for bigger numbers. Just a whole bunch of weird things. And you see the case they were actually passing sort of realistic looking addresses in some cases. So that's all sorts of strange things like. So open is a more complicated case because one of the arguments, it takes certain types of values. It needs to be one of these values, otherwise, or a combination of these values, otherwise it's going to just reject the system call immediately. So in order to make this succeed, we pass it some valid values, then we can reuse the results of this in future system calls. So we have these lists, and because we have 300 or so system calls, it took forever just to annotate every different system call and add these lists, and I still haven't done complete coverage of everything yet. And again, every time I'm adding more coverage, so more information about system call, it seems to be turning up more fun. Coming back to the addresses. So addresses, we go back to that function where I was telling you about the interesting values.
Yeah.
I'm trying to do boundary situations, but
I see.
asking about that. So is that cover your question?
Yeah.
As well as that, once started, we read proc-self maps and just gather a whole bunch of addresses from there. There are certain things that get avoided deliberately because you don't want to corrupt yourself, otherwise you just say false. Certainly.
I was asking just on that note, do you use like sub-processes for that reason? Like you
Yeah.
use like
So when it runs, the actual system call is done in a trial because it may seg fault, it may just do something completely horrible. Or worst case, it may actually hang.
Yes.
A lot of system calls, if we pass crap into them, there's hanging definitely. So we set an alarm clock for that, and if the syscall hasn't returned in 3 seconds, I think it is, then it kills the process, and then we just move back around again, spawn a new child, start again.
Are you retracing them, or are you not?
Not doing retracing. And something that I thought about just to screw with things even more, just really throw a spanner in the works.
Yeah.
Just one of the things I haven't got around is I have to do this for this one, so it's ridiculous. So I'm flying is a little faster than I anticipated, but I'll give an example of some of the bugs that this has found. So I'm giving like a kill list of things that it's found. So the interesting thing is that it's not just system call bugs that's actually turning up. It's the effect of actually calling system call changes enough state in the kernel that certain things get very confused, and sometimes you get all kinds of side effects happening. We've also found a bunch of other really silly things like world writable ACPI file system NSFS, which when you put complete garbage in, the ACPI interpreter will try to execute it as if it was ACPI AML. This didn't end well. And this was world writable, so any user could do this, so not really a good thing. So that got fixed up a while ago. A lot of bugs I find is just noisy spew, just back traces, where it's not actually a fatal thing. It's just whoever wrote the system calls never envisaged that the user input to the system call may actually be hostile, so it just lacks certain validation. So there's a number of bugs that's found like that, which is completely benign, but it's just noisy and still a key message. So a bunch of those got fixed. A fun interaction one was I actually tell the tool just to focus on a specific system call, and one day I told it just to do mprotect. So it spent like 12 hours or something fuzzing mprotect, and it wasn't doing anything. I had this running in another window, completely forgot about it. And I was working on something else, and I ran the perf performance testing tool, and immediately got loops. And there was a race condition between mprotect and perf. When perf started up, it was actually taking a snapshot of every process in the system. And there was just a really weird interaction between the two important loops. But it was something that, it would be one of those situations that would be very hard for you to actually explain what the hell just happened if you stumbled across this loops. It's just one of those really sort of obscure edge cases. Well, there's a function called pipe F control, which is called as part of the F control system call. If you, I can't remember exactly how this worked, but if you passed a pipe, if you passed an FD which wasn't a pipe, like a socket, for example, to the F control system call with flags that told it to do pipe operations, it would attempt to treat that socket as if it was actually a pipe. And that was another simple boost, so that actually took quite a bit of fixing and refactoring the code. Another case of system calls truck being trusting their input. NTP users could basically adjust the system clock just by calling a certain system call with cracking in the arguments. And I found this completely by accident one day when I noticed that my clock had jumped forward 4 years or something. Yeah, that was an odd case. So a lot of these bugs they've been around a really long time. That just scares me. When you look at the NTP case, that had been there pretty much since we moved into the code to actually talk NTP to adjust the system clock. It found out actually a lot of bugs where the kernel would just get really, really confused. Because it just does this tight loop which is just causing the kernel, it spends so much time in the kernel, it can actually cause line locks in some situations. And there was one specific case where we would actually fill up the TTY buffers, and the TTY buffers would never get to purge the buffers because there was constantly more input coming in, and it would just totally freak out. And even after you quit the tool, the kernel would still be running at 100% CPU time. And that was a really awkward bug to diagnose because you could run top, wouldn't show anything. You could even run perf top, and you wouldn't really get an idea what's going on. To debug that way, the time to use the ftrace stuff that's added fairly easily, and actually examine the workflows to realize just to figure out how much work was actually integrated, and see where the time is being spent. It's turning up a whole bunch of networking related bugs as well. Because of the random socket creation on startup, when you open a socket, the first thing the kernel does is looks up to say, do I know how to support this protocol? If it doesn't, it loads the module to support that protocol. And it turns out that a lot of the really obscure networking things like DECnet and SCTP and a whole bunch of other lesser used stuff, it turns out that sometimes I don't think they're getting the coverage that a lot of people think they are, because we're making changes to those where people are applying just what looks like simple cleanups and completely destroying things like the logging. And a good example is SCTP.
SCTP is the 27.9.
Yeah. Oh, that was a thing, but I'll come back to that one. I'll give you everyone's example. The earlier case, as soon as you load the module, the init path of the module, the first thing you did was take a lock, do some initialization, and then release the lock. Someone applied a cleanup, which was of dubious value. It was as a result of the removal of the big kernel lock. And in the result of this cleanup, they missed one case where in an exit path we were doing an unlock. And this case actually was fairly easy to trigger, so just loading the module in a lot of cases was enough to get backtrace. But no one reported this, and it'd been that way for over a month. So in that month, either no one with the debugging options in the kernel enabled had loaded that module, or just no one ever reached the message. So there's a bunch of other similar ones. SKTP was another really peculiar thing where we weren't doing, there was missing bounds checks on what we were passing down to the sockets. So it ended up trying to do these absolutely enormous allocations, and you wouldn't initially see this as an SKTP bug because you see things like the OLM killer or the page allocator failing to allocate pages. See all kinds of weird VM things going on. The most recent thing that's found, which took a lot of digging, was some of the network modules. They were treating sizes of packets as signed integers. This led to some really strange things where you're trying to allocate packets with a negative size, which means absolutely enormous packet size. So again, that was another thing where we just seen page allocated, just going absolutely crazy and just freaking out because we couldn't allocate stupid amounts of memory. There's a bunch of other bugs that is tickled that we're still trying to figure out. Another really the strangest one of all is an IP routing bug, where it's actually trying to, it ends up trying to route an outgoing packet using the incoming variable, or vice versa, I forget which. But this has the networking people scratching their heads right now, because no one's quite sure what's going on there. We've seen some back traces, but no one's really got a clue what's going on. So that's pretty much what the tool does and what it's been doing. I don't think I have any more examples. Oh, there was one thing that I asked. So the annotations for system calls, as well as annotations of flags, there's one magic kind of parameter that is a standardized argument. And what that does is, after applying all the generic things like the argwen and argres that pass realistic values, it then calls the function that's passed as that argument. And that function it can do anything. It takes exactly the same arguments as the actual system call, and basically you should manage that to whatever you think will get you further into the function. Some of these have a lot to do. There's actually only about a dozen or so system calls that have standardized arguments right now. I hope to find time eventually to add them to more often, because it's another one of the situations where every time I add one, I seem to trigger some great big bug. That's basically it, I think. Any other questions for that?
How did you find that sysfs?
The async sysfs bug was found, the machine just completely went black. Display completely went. Fans in the machine started roaring. When I powered off and powered back on, the machine didn't come back on. I had to reset the CMOS in the computer just to get it from booting again. It really, really got upset.
So how did you find out which syscall?
So it creates a log. Before it makes the actual syscall, it logs the syscall and the arguments. So it does the same as well, make sure it does actually hit the disk before it ends up crashing or something. So fortunately, I was able to just look at the log and you say, oh, we did a read on this file descriptor. What was the file descriptor? /syscpi. Oh, okay, yes. And then just as soon as I looked at that file and saw the permissions were, worldwide, duh. So sometimes it's that obvious, right? A lot of other times it's a real head scratcher. What the hell just happened? And sometimes you cause a crash and you look at that last syscall that happened, you can rerun that and it won't trigger the same crash because it's dependent upon state that you did in other random system calls before that. So you don't have to try to narrow it down by replaying a subset of the log or just code inspection.
So supposing your syscall is done something nasty like that, but it's not so obvious straight away, and you notice a few hours later that you just changed to become root or something like that. Then how do you track that?
There's been one or two cases where I've run the tool and something strange has happened and I haven't had any idea whatsoever. And I've tried to debug it and I just used to be completely lost cause. I've tried to repeat it using just looking at the log and I haven't been able to get to it. The only way that I've really been able to diagnose some of those bugs is on subsequent runs I may see it again sometime and it's like, oh wait, this happened recently, and comparing two logs, that's happened once or twice where I've been fortunate that I've been able to see, okay, we've got MTech here and MTech there, what's common between them. Other than that, there's no real sort of silver bullet. It's kind of, if something bad happens, we're relying right now on things like the kernel debugging, things like the slab debug checking and linked list debugging, just to make sure that if something in the kernel space gets corrupted that shouldn't, the kernel usually should dispute something, say, hey, this is terrible, something bad just happened. With regards to writing, doing things like changing the UID, I could add a check in the tool to just check the UID every time we return to the system call. But what else we want to check? There's probably a dozen things you need to check.
More than a dozen?
Yeah. Right.
If you put any thought into an automated log replay, so you can just replay certain portions?
I thought about it, but it's just another one of those. I'll get around to those one day. Something else similar that someone suggested was actually being able to replay S-trace logs and then just kind of twisting the arguments that S-trace passes prints. That could be an interesting tool, but it's another one of those sort of rainy day projects that I never get right.
Are you putting it in VM and running it through?
What, sorry?
Like in VM and running it through?
I made the mistake of running it as a group once, and it was a similar situation to how I just described the ACPI, where it locked up the box completely. So don't do that. It actually does a check first thing, and as soon as you run the tool, it checks if you're root, and refuses to run if you're root. So.
But as you say, you can run it in a virtual machine.
I have actually run it in a virtual machine.
You can run it with some kind of snapshotting, so every half hour, snapshot the virtual machine, save its state, and then if you fall over, you can say. So in answer to this question, you don't want to snapshot before you do everything, but you can snapshot every half hour, and you can say, okay, well, something weird happened in that half-hour window. I'll go back to like 2 hours ago and resume from there. And
the problem, one of the problems with running this root is root can do anything.
Yeah, right.
And so if it stumbles across, if it passes an FD of like /dev for example,
you're done.
Game over.
Yeah.
So there's so many sort of safety things you have to add to make it safe for root to run.
Try to be a VM generally, right? To a VM.
I think if you run this root in a VM, it would just kill itself very quickly.
I mean regular user, not root, just a regular user in a VM.
Okay.
Because you could that would be easy just for anyone to like run this without any risk on their system. Right?
Oh right, I see. I mean that should work. It shouldn't be anything special.
Yes.
You might actually find some hypervisor about that as well.
Right.
A long time ago, someone actually suggested doing a similar thing, but instead of for system calls, trying to fuzz Zen's hypervisor calls. In a lot of these sort of things, people just haven't tried doing crazy things with them, and a lot of time people eventually get around to trying crazy things. Surprise, surprise, it blows up.
I got a couple of questions, but if anyone's got, you go ahead.
To help you reproduce something, can you see direct number system with a known value?
Yes. Yeah. If you don't pass anything at all, it just uses the time of day, and it prints that in the log saying this is what I'm seeded with. But it will take a parameter, say seed with this number, so you can rerun the same run.
Any thought of running this in parallel, like multiple process testing?
Yeah, and that's found through things as well. There's actually a good bunch of, there's a few of the test scripts. There's a few sort of test harnesses, and this one, for example, does, you check how many CPUs you have, and it'll make sure you run one on every core that you have. It also has there's a 32-bit mode as well, which does 32-bit system calls in a 64-bit process. That also blew up horribly when we first started doing that. The 32-bit entry layer, not as well tested as usual.
You can combine that with the ptrace thing, right? Because that's how that two of those compact bundled just happened last year when ptrace was being used to call 32 bits as calls on 64-bit.
Yeah. When people have been calling the system call button, I've been trying to think, how can I make the tool reproduce that? Why didn't the tool find this already? And that's actually led to a few improvements. I know that. There's a similar tool that I was completely unaware of until almost like 3/4 done was where it is now. And there's a guy at Google who wrote a tool called I Know This. If you Google I Know This, you'll turn that up. And in many ways, his code's actually a lot nicer than mine, but his tool works in slightly different ways. So I think there's room for both of them to exist because we seem to be tackling different bugs. But we borrowed some ideas from each other to enhance it. level as well.
So the other question I was reading about architectures, right? So the different architectures do not only use different system calls, but they also have different system call table ordering.
Yeah.
And some architectures pass things on the stack. Others will use registers or handle like more than 6 arguments differently. Or there's a lot of differences there.
Okay.
Done multi-arch.
Good news. First of all, the argument ordering, the system call table ordering.
Right.
For every architecture we support, we basically have a copy of the system call table.
Okay.
And it just looks as you'd expect, just a list of entries to every system call, just points to the structures that I was showing you earlier. And that's basically all it is to it. So you have one of those for every single architecture. So ABC. So far it's been from x86, x64, RPC, i64, and Spark. Some of those they probably need to be updated and maybe tested again because it's been a while since they've initially brought it to it, and there's been so many changes to it now that I'm pretty sure they'll find something. The second argument,
register handling basically.
register handling. The actual code that does the system call, it's kind of ugly. So we have the nasty if we're doing a 32-bit system call, we end up just doing into APs like we're doing 32-bit.
So you don't just do the DSO, you just do that.
Don't touch the DSO at this point.
Okay.
As you see, 6 arguments, I was doing a stack-based arguments. I haven't gotten around to writing that yet. So
Right.
Every other case, we just call the syscall function. So that's pretty much irrelevant to architecture intent. So it'll do the right thing as long as GDC knows what to do.
Question back.
Yeah, go ahead.
Do you have anything in terms of IOPL based?
IOPL is the worst system call
Ever.
It's the reason it's hard for a tool like this to do IOPL is IOPL's interface is you can't really enumerate it. I've tried. The actual parameters that it takes, they're completely opaque and they mean absolutely anything depending on what the IOPL you're calling is. So you need a massive table of every IOPL that's implemented just to be able to pass the right thing. So far the tool just passes garbage and it hasn't found anything particularly interesting. It tries to be a little bit clever and pass things that kind of look like structures, where it just generate things with like here's a bunch of addresses and a couple of lengths. But I haven't found a single bug in IOPL yet because of this. It needs more intelligence. It needs a lookup table to know what it's calling and what it's expecting. So it's essentially a duplication of the entire tool. Instead of finding syscalls, it's IOPLs. And at some point I might actually get around to doing it, but doing it generically, like to try to hear it, it's pretty much a lost cause, I think. Kernel annotations, I've considered doing it a while ago, not for the IOPL case, but just for the system call case. Because coming up with these structures was like really time consuming. Just annotate the types and so on. It was a few hours work when I kind of changed the structure, design in some way. I have to start over and spend a few hours, looking at the kernel source and annotating it again. So it would be nice if I was able to run some script and just suck everything out of the kernel source and spit out, structures that I can use.
When you shell and C, does it compile? Like, is it taking these shell scripts and then taking this and then compiling stuff each time and running those? So how does it actually? What are the shell scripts you keep?
Well, the shell script is just calling the actual tool.
Okay.
Like it does this. It just basically does that in a loop.
Okay.
But it doesn't have magic to do like binding it to the actual ECU. Yeah, nothing really clever. There are some other test scripts that I came up with. create another process for every single system call. So you have like 300 processes all banging on a specific system call. What's the other one? There's a rotating one as well, so for example, which is just, yeah, it's nothing particularly clever. It passes different, the dash D passes a 0, and dash A passes a kernel space address, dash U is the user space address. So it just passes addresses to the rotating register.
So how long do you run this for drivers now?
How long can I run it for?
It fails or causes a problem.
Well, because we've been fixing the bugs that it's been finding, right now it actually runs pretty well. Actually, I was horrified to think that I could be given this demo and I'll be running it. It's going to be one of the crash when I give the demo or something. But I'm pretty confident right now that this is a 3.0 kernel and everything that's found, well, almost everything, has been fixed now. So it can run indefinitely at this point until I start adding more annotations and other sanitization routines. But it's still, I'm not sure.
Are you deciding if it's a success or a fail?
Just the result from the system call. Syscall.
Some arguments you would expect a failure return code. That is the correct thing to do.
Yeah.
So how do you say if it's correctly returning -1?
There's no checks for correctness. It's just literally reporting just what kernel returned. That's all it's doing at this point.
To enhance the testing, could you consider maybe every 10 minutes doing a thorough system checks of all file menus and just, top, for example, to catch more bugs?
I haven't thought about that. It's not a bad idea. Could do something like that. This is something that happens fairly regularly as well for some reason. The DNA debugging runs up memory and decides to disable itself. I think that's possibly another bug. But other than that, I haven't secured anything really nasty other than all the networking thing on the top, which when it loaded the modules, when it created the sockets. That's pretty much the only thing that's going on there. It's very dull and very boring. Some system calls are a bit noisy as well, like the DNA6 system call, for example, doing that for no good reason. Yeah. But the tool just carries on. Does its thing.
So do you guys have this running on test infrastructure now, or is this just run manually?
Red Hat is running internally on like RAL builds and such. So we have some automation down there. We're looking at, for a long time, the Fedora projects wanted to have a similar infrastructure outside of Red Hat. If that ever actually happens, then this sort of thing will be something that we would like.
It could be OTSP, it could be in the test project, right?
It could, yeah, it could do something like that. But because it's actually I'm still developing it at a fairly frequent pace. I'm not at the point of doing sort of point releases that they want to do snapshots of at this point. So maybe when I get bored of it and stop, working on some perhaps. Perhaps they'll be better served at than a different role.
Any thoughts of implementing some of this on the other platforms, which are more fragile tools?
Well, calling it to a different architecture is pretty simple. You just have to just give it the system call table order, and that's all you have to do. And tell it how the system call is actually made. If it's anything special, that's pretty much it.
Does Red Hat also run LTP?
Just a whole bunch of different test stuff that we run. I'm not sure off the top of my head which ones exactly, but there's a huge slew of tests that the RHEL stuff is. I don't work on the RHEL stuff specifically, so I'm kind of detached from that world. But there's teams that just do nothing but running tests and stuff like that. Any other questions?
Is there anything you've discovered that Black Hat would be interested in? Worry about the responsibility.
Well, things like that ACPI code, for example, that you could have used that for serverless escalations. Because the ACPI interpreter was just run by any password. So the ACPI interpreter is turbulent and linked. You can do anything you want, including writing one of its kernel memory. So
Just running them over.
Yeah.
I mean, there's denial service, but there's considered more serious things.
Yeah, the ones like that where it's actually being able to write to context, they're obviously the more concerning ones. The bulk of the things is found are more the general service, and they're all local denial rather than, well, most of them are local. One or two of them were triggerable permanently.
So if you find something like that, you can fix it, but you also perhaps not going to announce that you've fixed something recently.
I'm having two camps on that argument whether or not to label security fixes as such. I mean, I can see why. I see the argument of not understanding it that way, but the thing is, the fact that are reading the change logs and the patches anyway, they know these problems are there. So I don't really see the point in trying to cover it up after the fact. Just fix the bug and move on. That's my framing that here. Cool.
Would it be possible to get code coverage report of when running this tool?
That would be really nice. Something that I've been thinking of is trying to use the F-trace infrastructure to see just how deep into the system calls it's getting. Because for a lot of them, it's still returning invalid very early on because we don't have the standardizing routine to get to past sensible arguments. So yeah, some kind of code coverage tool like that would be a really nice thing. But right now, we don't really have. The closest we have right now is just running things like Earth and just seeing where time was spent. That's probably the closest we get right now.
Any thoughts of running these tests while the system is stressed with the bug process compiled for your
Yeah, I've tried a whole bunch of things like that, where it's running other kinds of fuzzing tools and kernel builds and benchmarks, all kinds of things, just really fogging everything down. Sometimes it's actually, some of the bugs that we found, they're really awkward to get out. I mean, you have to really push the system to its limits to tickle some of these bugs. And those are circumstances are exactly when it's, one of them, I think which one of the ones that I've worked on recently, the machine had a load average of like 100 or something for a day solid. Because there was so much crap going on. And it eventually inspired the trace that I was looking for.
What's the license?
This is GPL. Yeah.
Was this inspired by what the processor vendors do with the hardware, where they just throw random bit streams at the code to see if random opcodes that don't exist do stuff? Where did you get the idea?
Well, the initial idea came from the tool that Kurt Goff wrote that I mentioned earlier.
Wow.
With that.
So you just got frustrated with it? You wanted to
Yeah, I mean, Kurt's original tool was actually called S-crashing, and the tool you're talking about, the running random opcodes, that was called crashing.
Okay.
So it was obviously inspired, at least the name by that. But Kurt's thing is very, very basic. That's 122 lines of code, and it just didn't do a lot at all, just calls and random system calls. Completely random on this. That's it.
Have you looked at exploits in the past few years to see whether this could be the good conditions?
I've looked at Ethereum and tried to, in some cases I've actually reversed the fixes that have been applied to the kernel just to see if it would tickle them. And when it hasn't hit those bugs, I've then tried to improve the tool in some ways. The number one thing that it needs more work on is just more annotations of the cleaning up of the arguments before it gets passed. And that's the number one reason that it hasn't found some of those so far. It just needs someone to sit down and have a time and just fully annotate every system call.
And the pages you fill with numbers.
That's something I haven't thought of. Actually, not a bad idea. There's no executable code at all right now. It passes zeros, all FFs, or just completely random garbage. I haven't thought about passing code to it, but that might be interesting. It has to be terrifying if that turns out to work, because that will obviously be trivially exploitable. Sorry?
That's code that no machine will do the junction to your kernel factories.
Yeah, that'd be an interesting thing to do. Yeah, I think I'll look into it. I might actually do something just to see. I've got my mind at rest, if nothing else. Hopefully it doesn't break anything. I feel a little scared now. Any more? Okay, guys, am I voting in my time?
Yeah, you're out there.
I'm out of time? Okay.